try to figure out the formulas, okay, which we are using. So just let me share the screen. I think all of you can see my screen. So let's quickly recap what we discussed in the last class. We were discussing basically the current which is flowing. This is Ohm's law that you are very much familiar from your physics. Okay, so the current which is flowing is basically proportional to a voltage, and the current which is flowing is inversely proportional to the resistance. Okay, that we have seen. So I equal to V by R, right? Voltage applied upon resistance, that you know. Resistance is rho L by A. So Ibrahim, have you studied it? Jasleen, Ibrahim, in physics also have you studied, or you will be studying?
Yes, sir. Yes, sir. We finished the class. Current
Yeah.
electricity.
In physics also we are having this. So R equal to rho L by A. R is the resistance. And what is rho? This is the specific resistance. Clear? Specific resistance is the resistance per unit volume. Okay, per by 1 cubic centimeter. Okay, it is the resistance offered by conductor having cross section area of 1 centimeter square and length 1 centimeter. Okay. So it is just like per unit. That if you do the reciprocal, so this is clear. If you do the reciprocal of this whole formula, this become 1 upon R. This become 1 upon rho. Is it clear? And it becomes A by L. I just reciprocal the whole equation 1 upon R A by rho into L. And in this case, we can see this 1 upon R. What this 1 upon R is known as? Who will tell me? Jasleen, Aisha, Marwa, can you explain me what this 1 upon R is? Who is going to help me out? 1 upon R. R is the resistance. Okay. What is 1 upon R? Jasleen, Aisha, tell me quickly. Marwa, Ibrahim.
Is it conductivity?
It is resistance and reciprocal is conductance. Resistance is actually how difficult it is for the current to flow. Conductance is the ease with which the current can flow. The same type of name, resistance and conductance. Got it? So this is conductance, and this conductance is it is called by C or G. You can call it C or G. Okay. Some books use C, conductance, and some books use capital G. Is it clear? And 1 upon rho, 1 upon specific resistance. Okay. It is called kappa. Kappa is the, so that is specific, rho was specific resistance. So this is the reciprocal approach, that is specific conductance. It is the conductance offered by an electrolytic solution having cross section area of 1 centimeter square, or conductor having cross section area of 1 centimeter square and length of 1 centimeter. Wherever you have the word specific, that is means per unit, whether it is physics or whether it is chemistry. I hope this is clear.
Yes, sir.
Okay. And so this is G is the conductance equal to kappa. This is Greek letter kappa, specific conductance, or it is also known as conductivity. And if I take this kappa, if I keep it alone, I will take this L by A on the left hand side. And these are the length and the area, cross section area of the conductor. So this is basically related to the dimensions of the conductor. Is it clear? So this is known as cell constant. Is it clear? So I should write kappa equal to conductance. You should remember this. Kappa equal to Cc, conductance into cell constant. The abbreviated form Cc, I am telling it for conductance and cell constant. Conductance is G. And cell constant depends upon the dimensions of the cell. L by. Okay. Is this clear? So this we have seen kappa equal to Cc, conductance into cell constant. Just remember this. Okay. Kappa equal to L by A. Okay. Kappa equal to Cc. Just remember, very important. Lot of numericals will be solved by this. Okay. And kappa equal to conductance is denoted by G. In NCERT, they are using G. And cell constant is denoted by G star. Okay. So you can write kappa equal to Cc, conductance into cell constant, or kappa equal to Gg. Okay, Gg is conductance is G, and another G is for G star, that is the cell constant. You can remember this in words. If you remember this, and wherever you have the word specific, specific means for per unit. Okay, just remember this. Is it clear? So specific conductance is kappa, okay, or conductivity. It is the per unit length. Is it clear? So I hope the formulas are clear. So let me Let me take some numerical examples. Okay, let me take some numerical examples. And very simple, just remember the things which I told you and you will be able to solve the numerical. Let me write it. So this is a famous basic question, okay, from your in-text problems only, and very simple. So let me write it, the data for you. The measured resistance of a conductivity cell. Cell is the container in which you are doing your experiment. Clear? So basically, this is the value of R. Whatever the values you get, just collect them and write them clearly separately along with the symbols, so that you can have in your mind the formula which need to be applied. Or this is basically the resistance, and basically they are asking about the specific conductance. If the cell constant has the value of 1.25 per centimeter. So this is one part of the question. How we are going to attempt it? Jasleen, Ibrahim, Aisha, forward, tell me. Resistance is given, but a specific resistance is not given. Okay, conductance, specific conductivity or specific conductance is kappa they are asking. Ibrahim, what formula are we going to apply? This is a straightforward question. Ibrahim, tell me. What formula are we going to apply? Kappa equal to? Yes. CC. Yeah, Aisha, kappa equal to CC, conductance into cell constant, or GG. GG is G conductance into G star. Okay. Is it clear? So Kappa is conductance. Conductance is the inverse of resistance, reciprocal of resistance. Okay, and the G star is already given. .25 per centimeter. The unit is of this is, it is because of the inverse reciprocal of resistance, so it is 1 upon ohm. So ohm inverse, or you can write, you can invert the spelling also of ohm, mho, MHO. Got it? Or you can write S, and this has the unit of per centimeter. So kappa is going to be 1.244 into 10 to the power 3 minus 3 per ohm per centimeter. Is this clear? Kappa equal to Gg, Gg is G and G star, or Cc, conductance into cell constant, that's the mnemonic. So I hope this is clear to all of you. The cell constant remains same. Okay, the cell constant is remains same for a specific container. If you are changing the concentration, that will not change the cell constant. Cell constant will only change if you are changing the container in which you are measuring the conductance. Is it clear? Now we will talk about the molar conductance. What do you mean by molar conductance? Can any one of you help me out? What it means? What could be the meaning? Though I have not told yet. Yeah, Marwa, what could be the molar conductance? Tell me. Ibrahim, am I audible? Are you there? Jasleen.
Yes, sir.
So what do you mean by molar conductance?
Sir, like the conductance per mole of a compound, of any compound, conductance in 1
Yeah,
mole.
suppose if I put 1 mole of NaCl in water, it will dissociate. So whatever is the conductance of that 1 mole of NaCl, all ions furnished by NaCl upon dissociation, irrespective of its volume. Okay. So molar conductance is basically molar conductance of an electrolyte It is the conductance of all ions furnished by one mole of electrolyte. All ions I am writing because that it may dissociate. For example, if you talk about 1 mole NaCl, I will put the subscript. This is lambda. Okay, be careful. This is small lambda, and this is capital lambda. Is it clear or not? So this lambda is for the molar conductance. Means if you try to measure the 1 mole of NaCl, okay, so that is the conductance by 1 mole of NaCl, that is the molar conductance. Irrespective of its volume. Right? So suppose it may happen you can have 1 mole NaCl in a large amount or 1 mole NaCl in a small amount. Small solution concentrated also. Okay. The concentrations are different. But this is also known as molar conductance. This is also molar conductance. But they are not equal. Why they are not equal? Though both are molar conductance, but they are not equal because the concentrations are different. You have put 1 mole in both, but due to dilution, it may change. Is it clear? So what is the formula for molar conductance? Molar conductance is for complete 1 mole and specific conductance or conductivity. This was for complete 1 mole. And this is the molar conductance. And this doesn't, kappa doesn't bother about the mole. Kappa is for specific conductance or conductivity. It is the conductance of 1 cubic centimeter. Is it clear or not? There are 2 variables which we are having. So can you tell me, Ibrahim, how they are related? Aisha, can you tell me how they are related? Jaslyn, can you tell me how they are related? This is for complete 1 mole. And that is not for 1 mole, that is for 1 ml, 1 cubic centimeter. Can any one of you help me out? How to correlate them? Okay. Look at the figure over here. Very simple. This complete 1 mole has a molar conductance of lambda. Got it? And if you take 1 cubic centimeter, kappa is for 1 cubic centimeter. Lambda m is for complete 1 mole. So if I want to calculate the lambda m for complete 1 mole, I need to, 1 to many multiply. If you are having a value for 1 cubic centimeter and if you want to find the molar conductance for complete 1 mole, you need to multiply. Okay. Multiply by what? So this lambda m, if you see the figure over here, lambda m is for complete 1 mole. And for 1 cubic centimeter, it is kappa. I can get the lambda m for complete 1 mole if I multiply the kappa is for 1 cubic centimeter, into volume of this whole 1 mole. This is for 1 cubic centimeter. And if you want to find the molar conductance of total 1 mole, you need to multiply it by total volume. For 1 cubic centimeter, it is kappa. For total, it is kappa into total volume occupied by 1 mole of solution. Is it clear? And this total volume is 1000 in ml because we are measuring in ml by molarity. This is mole per liter. Mole per liter is basically tell you how many moles are there in 1 liter. Okay. So 1 mole will be present in how many liters? 1 upon m or 1000 by m. Jasleen, is it clear how the formula is derived?
Yes, sir.
For 1 cubic centimeter into total volume. 1 cubic centimeter, the conductance is kappa. Total conductance of 1 mole, you should multiply that 1 cubic centimeter conductance with the total volume. Total volume is, it is 1000 by molarity if you measure it in centimeter cube. And the kappa, as I told you, cc, conductance is 1 upon ohm or per ohm into cell constant. Cell constant is L by A, centimeter by centimeter square, so per centimeter. So the unit of this whole molar conductance is this is the volume per mole. Got it? This is total the 1000 by molarity is the volume per mole. So centimeter cube by mole. Is this clear or not? Any doubts in this? How the formula is derived? This is very simple. You need to multiply the specific conductance with total volume of 1 mole. Total volume of 1 mole can be obtained by 1000 by molarity. That's it. Very simple. Okay, and you can do the questions with this. Let me take one example. You have filled a cell. Cell means a container, okay, in which you are doing the electrolysis. So the resistance of a cell containing 1 mole per liter, 0.1 mole liter of KCl is 100 ohm. So if the same cell is filled, it is emptied. Original solution is emptied and a new solution is put. Mole per liter or capital M you can write. If the same cell is filled with 0.02 molar KCl, its resistance become 520 ohm. This is the value of new resistance. Earlier the resistance was 100 ohm. Now the resistance is 520 ohms. Cell is same, the dimensions are same. So the cell constant is going to be same. You have to tell me the conductivity. Conductivity or a specific, I am writing from my own side that it is specific conductance. Or kappa. You have to find the conductivity, specific conductance or kappa of this solution. You have to also find the molar conductivity. All these values are same. Just the name is different. I'm writing the symbol I'm writing. You have to find this and molar conductivity. So Ibrahim, is it clear what the question is asking?
Yes, sir. Yes, sir. We have to find kappa.
Yeah, we have to find kappa and we have to find the
Lambda.
molar conductance of
Molar.
complete 1 mole. Okay, molar, whole that 1 mole solution, how much is the molar conductivity, that we need to figure out. Is it clear? We need to find the kappa, that is for 1 cubic centimeter. Molar means for complete 1 mole. But you don't know how much that 1 mole is occupying. Is it clear? So Aisha, just try to do it. Nestlane, Marwa. So, but initially the data is given for 0.1 molar ACl. Resistance is 100 ohm. So how we are going to do it? Just tell me.
So we calculate the conductance G.
Yeah, we calculate the conductance G for this. G is 1 by 100. Yeah. Now what else? G, and there is one more data I think is given. I have missed that data. The resistance offered by this is this much, and the kappa. This is the value of kappa also they are given for this. For the first cell, they are given the two values. I hope all of you can see the question. For 0.1 molar KCl, they have given the two values. They have given the resistance, and we have already used the resistance to find the conductance. And they have given the kappa also. So this cell was completely emptied and filled with another solution. Another solution is 0.02 molar case. So everything will change. Resistance will change, kappa will change, molar conductance will change because the concentration is different. Is it clear? The only thing which is going to remain same between the two solutions is the solution is emptied and new solution is put into the same container. So what is going to remain same? Aisha, tell me. Point 1 KCl is emptied and 0.02 moles of KCl is filled in the cell. So the geometric dimensions are going to remain same. Is it clear?
Yes.
And if the geometric dimensions are going to remain same, but the solution has changed, the cell constant is going to remain the same. So we know kappa equal to Cc or Gg, right? G into G star. G star is the cell constant. Okay, this is 1 upon 100 G, and G star is cell constant. So G star is equal to, that will be equal to 100 into kappa. I will cross multiply. So kappa is 1.29 into 10 to the power minus 2. Is this clear?
Yes, sir.
Okay, so
Yes, sir.
and now the cell constant we are going to use it for the other solution. Now we have this, but the cell constant is going to remain same because the cell is same, only the solution has changed. So this is going to continue for 0.02 molar KCl. Okay. For 0.02 molar, the resistance is 520 ohm. Cell constant we know. Okay, now what is kappa? Kappa equal to G into G star. Conductance. As this is a new solution, the resistance is 520, so conductance is inverse of the resistance. And the cell constant is going to remain same because the dimensions of cell are same. Cell constant is 1.29%. So this is the new kappa value. Is it clear? Jaslene, Ibrahim, what happened?
Yes, sir. It's clear.
Yes, sir.
So this is new kappa value. Aisha and Bharat, and this is new kappa, and we are going to find the molar conductance lambda m for this new solution. So molar conductance is the specific conductance You need to take the specific conductance for this solution only, okay? Because there are two solutions. The earlier solution was used to calculate the cell constant G star, okay? And we have found the kappa, and into volume, total copper is just for one conductance of 1 ml, 1 cubic centimeter. In order to find the molar conductance of the complete 1 mole, you need to multiply it by volume of complete 1 mole. That is going to be 1000 by molarity. Okay, that is the volume in cubic centimeter. So new kappa is 1.29 divided by 520. We have it above. This is the new kappa value into 1000 by molarity 0.02. Okay, so we are getting answer of this is approximately 129 by 520, okay, into 1000 by 0.02. This answer which we are getting is around 124. Just you need to check it once more, the value, but you need to understand the concept first, then you need to put the data, because there are a lot of terms. So it is like a novel, Russian novel, where you have a lot of names. Okay, sometimes you have a lot of people in the novel, you forget the story is about which person. Okay, this is just like the same condition is there also. You have kappa, you have r, you have 1 upon r, that is g star. Okay, so many names are there. You have lambda, molar conductance. Molar conductance is for complete 1 mole. That's it. That is very simple. It is equal to kappa into volume of the 1 mole. Volume of the 1 mole is 1000 by molarity. This you need to remember. So I hope this will, all of you will do it correctly, because always you have a question on this. Marwa, is it clear? Any doubts in this? Aisha?
Yes, sir.
Ibrahim? Just remember lambda equal to kappa into 1000 by molarity. Okay, and kappa equal to g into g star. Just remember these two formula, you will have all the questions solved. Okay, so now let me move ahead to the molar conductance. This we have already studied. Molar conductance, I will try to focus on the molar conductance, not on the equivalent conductance, because the equivalent concept is not there. Okay, so we are going to focus only on the molar conductance. Equivalent conductance is one equivalent of the substance if you take. Okay, that is the conductance of one equivalent. Okay, so there you are going to use the normality, 1000 by normality, if you have equivalent conductance. So normality give you the equivalents per liter, but equivalent concept is not there. Mostly we are bothered about the molar conductance. So as I told you, is the conductance of electrolyte containing 1 mole of, or all ions furnished by 1 mole of electrolyte in a, okay, liter of solution. So kappa into volume of 1 molar volume, 1000 by molarity. Is it clear? 1000 by molarity is the volume of 1 mole. 1 gram mole is 1 mole, okay, of electrolyte. Now we are going to discuss the variation of molar conductance. Okay. So before we study that, let me ask you a very simple question, and that will help you to understand the numerical, okay, very quickly. Suppose if I have NaCl, one mole NaCl, let's say in 10 ml, or 10 ml is 0.01 liters. you have, let's put some water in it and let's dilute the solution. So if you put water into it, what will happen? So basically what we are doing, as you can see here, that we are putting more and more water. Is it clear? We are adding, you have just one more. Okay, I think we have to end the class, right? As there are some physics classes. Okay, we are going to discuss it in the next class. Okay, molar conductivity. So it is going to be, we are going to cover it on the next time, right? Because some of you may be having physics class, right? Is it clear? So just try to think what will happen to the molar conductance and the specific conductance. Okay, and how the molar conductance is going to change. Okay, let me tell you very quickly. The kappa is the specific conductance that is going to, that is 1 cubic centimeter, that is going to decrease. Okay, and the molar conductance is going to increase. We are going to discuss this in next class. Okay, so let me end the class. Just revise it from your NCRT and we're going to discuss it in the next class. Okay, right? So bye bye everyone, take care, good night.
Thank you, sir.
Okay. Bye.
Thank
Bye.
you, sir.